Welcome to my NEA testing video for my decision math program. So what I'm going to do is basically I have a selection of questions from past A-level past papers, and I'm going to input these into the program that I've made. So let's start the program. Here's the main menu. You have simple algorithms, graph algorithms, and then you have a how-to section. So first let's test simple algorithms. So here you can input the list. So as you can see, I'm going to input the list that we have. So this is also, this list is from a past paper question as well. So now with this list we can do an ascending bubble sort, and basically as you can see it has the list, it displays the list after each pass, how many swaps, and then it says no swap sort complete. These are all the steps that you need for during an exam to include. You can also do descending, and again it does the bubble sort, four swaps. It shows each pass including the blank pass. And so yeah, also there's error handling here. For example, if you were to type in a letter, it says item 1a is not an integer, it has to be an integer. So now we needed to test the bin packing as well. So the bin size we're going to use is 300 for the question that we've chosen. And first of all, you can calculate a lower bound, which uses the total weights divided by the bin capacity. You have the decimal, it rounds up, lower bound equals 4, correct? First fit, it packs the bins, it displays bin 1, bin 2, bin 3, bin 4, just how it should be. And first fit decreasing, it carries out the bubble sort, displays all the steps, and then after the sorted list, it carries out the first fit bin packing. And so yeah, all of this is working perfectly fine. Now let's go ahead and test the graph algorithms. So here, as you can see, you can add nodes. Nodes can only be one letter. You can't put a number as a node just to match how exam questions are. So yeah, and you can delete a node here, but obviously if a node doesn't exist, again node must already exist. But yeah, let's go ahead and input the question from the past paper. You have A, B, S, Y. This is like a scrollable frame, you can zoom out, zoom in, etc. And also it automatically capitalizes the inputs. Again, everything has been made to match exactly how the past paper questions look like. And so yeah, let's, as you can see, you can delete the edge like this. For example, I want to delete the edge S and L, it deletes it, and then I can add it back again if I want to. But if I was to delete an edge between S and A, because it doesn't exist, it says edge must already exist, so that doesn't work. And A and S 26, S A to L should be 54. And then basically you can input the graph like this, any type of graph. You can use a past paper, input a graph, and it's going to output the solution with all of the steps that you're required to include in an exam. So again, so now if I try to make an edge between two nodes that don't exist, it returns an error message. This graph is quite big. Again, and in the same way, like I said, if I try to delete like node Z, which doesn't exist, it's going to say node must already exist. So we can use this interface basically to make a graph, and that graph can then be used for any of the algorithms. You have Kruskal's, you have Prim's, you have Dijkstra's, and just finishing up the graph from the exam questions. Usually in exam questions, these questions like Kruskal's and Prim's and Dijkstra's are worth a lot of marks. So there's a lot of working involved, and the objective of the algorithm is of the program is to display all the steps that students need to include and not just the final solution. Now we're just finishing off. B to S is 34. A to B is 6. Now, and C to H is 17. Now we've constructed the graph. Like I said, you can move around these nodes, these edges are there, all the edges, the weights are labeled, and so now, yeah, you can go ahead and click Kruskal's MSG. It displays the solution. As you can see, it displays all of the steps. You have the graph here so students can visualize, but also you have the edges sorted first. You have the accepts and reject, accept this, accept BP, and whatever, and it rejects them if it causes a cycle. And then at the end, you have the MSG, the edges, and then the total weight is also written out. Now let's go ahead and try prims on the same algorithm, because the working is going to be a bit different and the MSG might be a bit different. Yeah, as you can see, the MSG again, it's displayed for students. They can move around the nodes, but it's a read-only version, so they can't edit it. You have the MSG written in the order of selection, and then the total weight. Both of these, for Kruskal's and Prims, that's the working you need to get full marks. And once you do all of that, then you can get full marks. Now you can clear the graph like this as well. And as you can see, the graph's been cleared. Now we're going to test the Dijkstra's implementation. You have A, B. Again, I've made sure to get these questions from past papers to make sure that they follow exactly how the mark scheme wants the working to be displayed. Again, just to show the nodes don't exist, there's error handling for that. And you can construct the graph like this: A to E, E to H. Let's weight 5, J with weight 7. As you can see, the edges might overlap in some questions like this one, but again, what I've tried to do is make it possible for the user to move around the nodes, which makes sure that they can read all the edge labels and so on. And you can go ahead like this, add the whole graph. We could have even used the MSG graph and use the same graph and do Dijkstra's on that, but I've used a specific Dijkstra's question. And Dijkstra's is the one, to be honest, it's the most difficult one students usually struggle with. It involves a lot of working, and you need to display the working values, the final values, the order of labeling, and there's a lot of working involved. And for each node, there's basically a table that needs to be made with all of those things, and so I made sure to implement that as well. B to F should be 5. And A, C, G, D, D, that's one of our last nodes. Now that we've added this, we just need to do DG is 6 in the question. A to D is 17. And then C to D is 9. As you can see, I've constructed the graph now. Everything is exactly as it is in the question. You have the edge weights labeled in the center, which also actually involves a lot of trick. But yeah, now we're going to find from A to J the shortest path. As you can see, you can go that way, that way. So then we're going to do Dijkstra's. And here you have the matrix as well. You can scroll through it, and it's dynamically updated as well. Now here you have the shortest path A, B, E, H, J. As you can see, it's written out, the total weight, and then you have the tables as well that you need for each node, the labeling order, final value, working values, 8, 5, 17, 14, the whole list. And again, this working will be enough to get you full marks. So you can clear the graph like this also, and let's return to the main menu. Thank you very much.